Alright, so Chapter 10, Re-expressing data. So we cannot use a linear model unless the relationships between the two variables is linear. Okay? If the relationship is nonlinear, which we can verify by examining the residual plot, we can try re-expressing the data. Then we can fit and use a simple linear model. To re-express the data, we perform some mathematical operation on the data values, such as taking the reciprocal, taking the square root, or taking the logarithm. For example, consider the relationship between weight of cars and their fuel efficiency. Miles per gallon. What did the scatter plot and residual plot reveal? Well, if you look at this, this is curved, and you have a U-shaped residual plot. Okay, so what do we know? Well, we know the linear model is not appropriate. Okay? So if we take the reciprocal of the y values, so that's over here, this is in gallons per 100 miles, and we get this scatter plot and this residual plot. So what do we know? Okay, well, we know that the relationship between weight and gallons per 100 miles is linear. Okay, that's straight enough, and that shows no pattern. Okay, so why do we re-express data? One reason is to make the distributions of a variable more symmetric. Okay. So if we know that one of the variables is skewed in one way, we want it to be symmetric. The second reason is to make the spreads, or the variation of several groups, more alike. Okay. To make the form of a scatter plot more linear, this is apparent in what we just did. Okay, what did we do? Well, we had a curved relationship, we want a straight relationship. And then to make the scatter and the scatter plot more spread evenly. Well, what happened there? We didn't have an even spread here. Those are called your residuals. Here we had an even spread. Okay, we had a bunch above, a bunch below, and it was clearly more random. So that's more acceptable for us. Okay, so just a little bit of review of math. So we got to find y predicted when x equals 3. So in the first case, we get this, and we get y predicted is 3.8. Okay, that's fairly simple. Then we do ln of y predicted equals 2.3 plus 0.5 times 3. So the natural log of y predicted equals 3.8. Well, how do you undo natural log? Well, you got to do base e undoes natural log. So you do base e to both sides, and that gets rid of natural log. And if I put that in my calculator, base e is second ln, and I'm going to do e to the 3.8. And I get 44.7. So y predicted there equals 44.7, because now we're dealing with a natural log. Next one is the square root of y predicted. Now if I put a 3 in here, I'm going to get 3.8. But I want y predicted by itself. Well, how do I undo a square root? Square both sides. So y predicted equals 3.8 squared. comes out to 14.44. And now we got 1 over y predicted equals 3.8. Okay. So I'm going to multiply both sides by y predicted. That crosses out. I get 1 equals 3.8 y predicted. And then to get y predicted by itself, I divide by 3.8. So I got to figure out what's 1 over 3.8. And y predicted is 0.263. Okay. Now I got log log. Okay, so log of y predicted equals 2.3 plus 0.5 times the log of 3. So in our calculator, we got to do 2.3 plus log of 3. I'm sorry, plus 0.5 log of 3. And that comes out to 2.539. 2.539. So log of y predicted equals 2.539. And undo log, we do base 10. So I do 10 raised to that answer. And I get 345.59. 345.59. And then we get y predicted equals 2.3 times 3 to the 0.5. So in this case, we do 2.3 times 3 raised to the 0.5. And then we get 3.98. Don't have to do anything else with that part right there. Okay, so that's how you would solve for y predicted given, there's a line, there's natural log of y, there's square root of y, reciprocal of y, log x log y, and that right there is a case where this is an exponential model. So it's a little bit of review of math that we're going to need going forward. Alright, so what we're going to look at now are some methods for re-expressing data. And these are not, this is not the only way you can re-express data, but for our course this is basically going to be some of the different methods we'll use. So we always start out, this is basically the ladder of powers, and this is what we're going to do to the y predicted variable, and this represents the exponent. So this is really our starting point, and this represents y to the first equals a plus bx, and that you guys already know, it's y equals a plus bx. And what is that? Well, that's a linear regression. Okay, so if we don't have to re-express it and it's straight enough and our residual plot doesn't show a pattern, then we have a linear model. We don't have to do anything. So this really isn't a re-expression. Okay. Now going up the ladder of powers, this would be y predicted squared equals a plus bx. And if we were to undo the square, we would really have y predicted equals the square root of a plus bx. Well, the calculator model does not have a square root function. So this one has, this one does not have a re-expression that you could use on your calculator. Okay. And then this one right here is y predicted to the 1/2, which is really the square root equals a plus bx. Well, if you were to undo the square root of y, what would you do to both sides? Well, you would square both sides. Well, if you squared both sides on the other side, you'd really wind up with a quadratic model. So this is quad regression, because this would really wind up being y predicted equals the quantity a plus bx quantity squared. This one up here would be y predicted equals the square root of a quantity a plus bx. So this is a quad regression, and then you would FOIL that and you get a squared plus 2bx plus b squared x squared, which you don't have to do for this course. Don't worry about all that. I'm just pointing out that some of these are on a calculator and some of them aren't. Well, if you were to just do y predicted to the 0 power, anything to the 0 power is 1. So you would have 1 equals a plus bx. Well, you can't have an equation with a explanatory variable and a response variable that only has one variable. So really what this is the log function in disguise. So what this is log of y predicted equals a plus bx. And that log function in your calculator is called the exponential regression function. And I'll show you where these are. Okay. Now we get a negative exponent. Well, what does a negative exponent do? Well, it moves it down below the fraction bar. So this is really, we already know y to the 1/2 is the square root of y. Well, a negative is 1 over the square root of y predicted equals a plus bx. Okay. And I'm not going to bother re-expressing all that. We would just leave that as it is. We don't have to do much more with that. Okay, and then -1 would be 1 over y predicted to the first equals a plus bx. These are your reciprocal. Okay, these are all the reciprocal re-expressions, and then this would be 1 over y squared equals a plus bx. And none of those have a function in your calculator. Okay, so these are all of your reciprocal re-expressions. And all of these are things, this whole ladder is what we're going to do to the y variable. Okay. Well, what if those don't work? Well, then we got to start dealing with the x variable. Okay. So what this becomes is, if we re-express log x, we get y predicted equals a plus b log x. Okay. And in your calculator, that is called, you could either do a log regression or a lin regression. Okay. And then this one's log x log y. Okay, so this is log of y predicted equals a plus b log x. And that's called a power regression in your calculator, if you were to do it in your calculator. Well, you're saying, Mr. O'Neill, what are all these things? Now, the attack of the logarithms are things that we're going to do to the x variable. Okay, or the explanatory variable. So these all involve the explanatory variable. This one involves both, and these up here in the ladder of powers only involve the response variable. Okay. Okay, so if you were to go to calculate a regression, you would go to stat, and you would go to calc, and then here's all your regressions, right? So there's your lin regression, or we go down to like number 8, there's your lin regression that we've been using. There's your quadratic regression, that's your 1/2 power, okay? So there's a quadratic. If we were to use a 1/3 power, which is not one of our re-expressions, though it is possible to have something that follows a cubic function, then we would use a cubic. Quartic regression would be 1/4 power, but we're not going to do that in this course. Okay, there's your lin regression. Natural log regression, not lin regression. Natural log regression is number 9. Exponential regression. Okay, so your natural log regression is your log x re-expression. Then you have your exponential regression. Well, that's this one right here, which is your log y re-expression. And then your power regression is the last one on the bottom, and that one is that is your log x log y. So these are different ways to re-express these. Just so you know that they go in your calculator, or how you can do it in your calculator. Though in this course, we're going to concentrate on doing some re-expressions, but really on the AP exam, it's not really about how well you can re-express data. It's going to be how well you can interpret re-expressions, and using re-expressions like we did here. You know, in the AP exam, they're going to give you re-expressions, and they're going to say, okay, well, go find out what y predicted equals given the model that we've come up with for this problem. So that's basically going to be the challenge going forward. So next we're going to head into doing some re-expressions, and we'll see how we put this into practice. Okay. All right, let's look at case 1 here. So if we put that into our calculator, it says an equation of the form y equals a plus bx is used to model linear data. Okay. So we have time in months and an account balance. Okay, and if we go to stat plot and we turn that on, we see that we have a fairly linear association. Okay. So in this case, our scatter plot is linear. If I calculate this, go to number 8, I get the equation predicted dollars equals 100 plus 10x. Actually, not x. We'll do 10 times months. Okay. Now that I've looked at that, kind of what happened is, as soon as I did that, my residuals recalculated. So all my residuals are 0, by the way. So this is a perfectly straight line, and I could tell that when I calculated it, because when I calculated it, look what r squared and r were, right? So there's absolutely no variation in the line, so there's no point in looking at a residual plot because there are no residuals. Okay, so in this case, yep, the relationship between x and y is linear. If for equal increments of x, we change a fixed increment in y. In this case, we're increasing. Okay. But this change can be an increase or a decrease. So in a linear situation, we have for every time x increases by 1, y will change either up or down by a fairly constant amount. Okay, so that's case 1. Alright, so let's look at this case now. If we put this into the calculator, and we do time in months and then our account value, and we go to stat plot and turn it on and do L1 versus L2, and then do zoom 9, we get a curved relationship. Okay, so the first thing that we're going to do is we're going to go use our ladder of powers. Now, whenever a function looks like that and we have to bend it downward, we're going to go down the ladder of powers. If a function looked like this and we had to bend it upwards, we would go up the ladder of powers. So in this case here, we're going to wind up going down. So the next thing we would do is we would do the 1/2. So let's see what happens if we re-express it using 1/2. And I'm going to do the square root of L2. So I just raised L2 to the 1/2 power. So the square root of 100 is 10. so forth and so on down the list. And I got to change my stat plot to do L1 versus L3 because I re-expressed y. And then I do zoom 9. And that is better, but it's still curved. So I got to go to my ladder of powers, and the next one down is log. So I'm going to re-express it. I'm going to close stat, edit, and I'm going to do log of L2. Okay, and now I already have my stat plot in L1 versus L3, so it's zoom 9, and that's pretty straight. So it looks like we're in a log function. Okay, so let's now let's see, we cannot use least squares regression for the nonlinear data because least squares regression depends upon correlation, which only measures the strength of linear relationships. Okay, we transform the nonlinear data into linear data and then use least squares regression to determine the best fitting linear model, or line if you want to put it, for the transformed data. So now I have to do stat calc, and I'm going to go to number 8, lin regression, and I have to do L1 versus L3. So my A value, my y-intercept is 2, and my B value is 0.0043, and I have very little residual here. I mean, I could check the residual plot since I just calculated that. Let me copy that equation down. So here is our new linear model. It's log of y predicted equals 2 plus 0.0043 times months. I did that wrong. This should not be y predicted. This should be predicted dollars. I don't like using X and Y, so this is predicted dollars. Okay, so log of predicted dollars. Now let me just check the residual plot. So once I calculate the least squares regression line, the residuals recalculate. So I'm going to go to second list and change my Y list to residuals, and then I'm going to do zoom 9. And that's pretty random, so I don't have to worry about the residual pattern. Okay. So we've got to use our model to predict how much we'll have in 100 months. So if I do log of predicted dollars equals 2 plus 0.0043 times 100, and I'm going to do 2 plus 0.0043 times 100, and I get 2.43. So log of predicted dollars is 2.43, and then I got to do base 10 to undo that, right? And so I do 10 raised to that answer, and I get $169.15. That seems to work. 100 months would be in here. It's going to be more than this and less than that. And that seems to be pretty reasonable since it's close to 96 months. So it seems like to be a pretty reasonable estimate. 250 months. So I do 2 plus 0.0043 times 250, and I get 3.075. Base 10 that, and we get 1188.50. And that's a problem because my data only goes up to 240 months. So this is 250 months, so this is an extrapolation. And is probably not reliable. Seems like a reasonable, it seems like a reasonable prediction, but again, there's no guarantee that this will continue. So that's an extrapolation, and we got to note it. Okay. All right. So in case 3, if we were to plot those, L1 versus L2, I put these into L1 and L2. There's the age and the weight of the rockfish, and I was to graph it. It comes out curved. Okay, so we're going to we're here. We got to go down the ladder of powers. So what are we going to do? We're going to say, okay, let's go down to square root of the list 2, which is the y variable. And we're going to do L1 versus L3 now, because we already expressed y. We didn't do anything with x. And we're going to do zoom 9, and that straightened it up. So now I do stat calc, and I do lin regression, and I do L1 versus L3, and I calculate it. And my y-intercept is 0. There's my slope, and there's my r squared, and there's my correlation. So this is a perfectly straight line. There is no residuals, so I do not have to go and check the residual plot. I already know that there's not going to be any deviations from the line. So this is what my equation is going to look like. Okay. Now I got to predict a 10-year-old rockfish. Now I'm not going to put that 0 in. I'm just going to put 1.732 times 10, and then predicted weight square root is 17.32, and then to undo square root, I square both sides, and I'm going to get predicted weight equals 17.32 squared. And let's see what happens when we do that. It's about 300. Okay, so it's about 300 grams. And let's see if that makes sense. 10-year-old, well, there's an 8-year-old. There's a 12-year-old rockfish, so 300 seems like a pretty reasonable estimate. So looks like we're good to go with that. Alright, so let's look at case 4 here. So if we put this into our calculator and we turn our plot on, and we go to zoom 9, we see we're curved. Okay, now I rescaled the data here. I put year 1800 as year 0. So in looking at this, I know we got to bend it down, so I'm going to start going down the ladder of powers. I'm going to do the square root function, and there's a square root of y. So I'm going to relook at the function, L1 versus L3, do 9, and that looks pretty straight to me. Let me see what log might do if I go down one more, log of L2, and then I look at it, and now I curved it too much, so log doesn't work. So it's got to be square root. Now, so there's our square root function. So we go to stat calc, and then lin regression, and we do L1 versus L3. And that's our slope and our y-intercept and our r squared and our r. Now what happens here is if we do the residual plot, if we put in the residual and we do zoom 9, it looks like we might have a pattern, right? So even though this is a pretty straight line, we had to decide now, is that random enough? Well, our other options are we can do the tactical logarithms, and that is we can check these two and see if either one of those work. So we can do log x and log x log y. So sometimes we'll check those. Let's just see what happens. Now, here's the problem with this one. If I do log x, I got a 0 in there. So what I got to do is I'm gonna just delete this for now. I'm going to change these back to what their original years were, since we started with 1800. So I'm just going to do, over in this list, I'm going to do L1 plus 1800. That brings them back, and then I'm just going to copy list 3 into list 1, and now we have our original years back. So now what I'm going to do is I'm going to do log of list 1, and then I'm going to say okay, let's do list 3 now, which is log x, and then let's do y. So that's log x y's. Okay, so let's see what that looks like. That's not good. Okay, so we only have one other option, and that is to do, we did log x in L3, we would do log y. So we do log of y in L4. So the L3 is log x, L4 is log y. So now I'm going to do L3 versus L4, and no, that's correct. So tactile logarithms didn't help us. So the best model we can come up with here, I'm going to change these back, is this is 0 and 25 and 50, 75, 100, 125, 150, 175, and 200. The best thing we could do is the square root function. That was right here. We did the square root of L2, and we did, this is x and square root of L2, and that was the straightest that we could get it. Now, you might say, well, you know, there looks like there could be a pattern in the residual plot. Well, sometimes these models are not perfect. When we look at our equation, which we already did, we calculated this. We're going to have an equation of the square root of population predicted equals 1.4688, and then plus 0.0744, and then this is going to be year since 1800. Actually, years since 1800, since we rescaled this, so we made this 0, and this was 25 and 50, 75, 100, 125, 150, 175, and 200. Okay. So, in this case, that's the best model we can do with the tools that we have. Okay. Now, it doesn't mean that there's not another model out there that doesn't fit it better. There might be. Okay. But our residual plots show there could be a pattern. So again, we might want to be cautious with this. Okay. However, we don't have a lot of variation because our correlation here is close to 1, and our R squared, which explains variation, shows there's not a lot of variation off of the least squares regression line. So most of the variation is being explained by this line, so that's a good thing. Now, that in itself does not determine if a linear model is appropriate, but it's an argument that we can use to say, okay, we're going to proceed here, even though our residual plot kind of showed a little bit of a pattern, we're going to proceed with caution here. Alright, so we need the residual for 1975. So we would do, we know that the actual for 1975 is 215 million. Okay, and then we need the predicted. So we got to put in, let's see, we're going to do 1.4688 plus 0.0744, and that's 175 years since 1800, and that's 14.488. So that's predicted population. Square root is 14.4888. Then we got to square that, and we get 209.93. So there was 209.93 million people predicted. So we subtract that. So our residual is 5.07 million people. Okay. So what does that mean? Well, it means it's positive, so that means this point right here is above the line. So there are 5.07 million more people in the United States in 1975. Actually, there's probably should be there were in 1975 than the linear model predicted. Okay, so that's it for case 4. So sometimes when we're doing these, we don't get perfection, but we get something that works pretty well, and that was basically the case here. Alright, so let's look at our last example here. So we got light intensity. So as the distance increases away from a light, then the candle power, which is how we measure light intensity, will decrease. Let's see what this guy looks like. Alright, so that's definitely curved down. So what we got to do with that is we have to now bend it down. So we got to go down the ladder of powers. So let's see what square root of L2 does for us. So I'm going to do L1 versus L3. Nope, not enough. Okay. So let's go down to the next thing on the ladder of powers, which would be log of L2. Zoom 9. Close, but not quite there. Let's see. Now the next thing we got to do is we got to do 1 over the square root. Okay, so let's see what that does. So I'm going to do 1 divided by the square root of L2, and let's see what that does. And that comes out to be pretty straight. Okay. So let's see if we calc this and we do number 8, and we're going to do L1 versus L3. Now watch out with this guy, because you see this A value here, and you see on the end here it's an e to the negative 5. That's the calculator's way of telling you its scientific notation. So that's like this calculator saying this is 5.54 times 10 to the negative 5th. So that's really negative 0.0000554. Alright, so you got to be careful with that. And then our y-intercept is this. So before I continue, there's not a lot of variation there when I look at r squared. So let me just take a look at the residual plot. So let's take a look at that. And that's pretty, you say, well, it's circular, but it's not curved, so that's a pretty random residual plot. Now there is another model that will work here, and I just want to show it to you, and either model would be fine. We can stay with that one, but if we go down to the ladder of powers here and we do log, which is this one right here on the bottom, log x, log y, I'll just show you that one. Let's see, we do log of L1 and then log of L2. So an L3 is log of X and an L4 is log of Y. And then if we go in and we look at L3 versus L4, no, that didn't work, did it? Okay, so that didn't work. Oh, I'm sorry. This is wrong. This is log of L2. Alright, so let's see what this looks like. There you go. So there's another model that would work, and if we were to stack calc that, so I'm going to do L3 versus L4. We get this, and we get a high R squared value there. And if we take a look at the residual plot, let's see. Yeah, so there you go. So kind of the same type of pattern, but it's just reflected. Alright, so there are two models that actually work here. Okay, so you're not wrong in using either one of them. Okay, so you could do the 1 over square root model, or you could do the log x log y model. So either one would be acceptable. So let's see what we get here. Since I'm on this one, I'll use this one, number 8. So one of the models you could use is you could use log of predicted candle power, like this, equals 3.3265 minus 1.999 times distance, log of distance, I'm sorry, log of distance, and, okay, and that should be in feet. So that's one model you can use, or you could go, we already checked this one out, but let me go to L3 here. I'm going to just delete these, and I'm going to say, okay, let's do 1 divided by the square root of L2. And if we go to stack calc linear regression and we do L1 versus L3, now this is the one with that e to the negative 5 that we got to watch out for, right? So this one would be predicted candle power 1 over the square root of predicted candle power, and we got to put that like that, and that equals negative 0.00005539 plus 0.02169 times distance in feet. And that should be in feet. Okay. Alright. So either one of those would be fine. Okay, you're not wrong in either one that you would use. Okay. So and then in the next ones that I do, I'll use one model to do one and the other one to do the other. So obviously, whichever model you chose, you would use the one that's you probably would have stopped here once you were on ladder of powers. All right, so let's do this one. We got 1 over predicted candle power over the square root is negative 0.00005539 plus 0.02169 times 12. Alright, so we got negative 0.00005539 plus 0.02169 times 12, and that is 0.26022,461. Okay, so we'll put that over 1, or we could just multiply both sides by square root of predicted candle power, like that. So that cancels. Then we would divide by this 0.26022,461. So I got to do 1 divided by this answer, and I got 3.8428 equals square root of predicted candle power, and then I would square that, and I get about 14.8. Approximately 14.8. So let's see if that makes sense. Well, the candle power at 10 feet is 21.1, whatever the units are, and at 15 feet it's 9.5. So 12 feet is in between those, and 14.8 is in between those. So that seems like a pretty reasonable answer. Okay. Now we'll do this one down here, and I'll use the second model. So we're going to do log of predicted candle power equals 3.3265 minus 1.999 times the log of 50. So I got to put this in the calculator. So we're going to put 3.3265 minus 1.999 log of 50. Okay, so we get negative 0.0697. Okay, and then what do we got to do? Well, we got to do base 10 to both sides. So I got to do base 10 to this answer. And I get like 0.85. Well, is that a reasonable answer? Well, we don't know. Our data only goes up to 25 feet. This is 50 feet. So this is an extrapolation. And is probably not reliable. Okay. So that's it for some cases that I showed you, just different ways of using the ladder of powers and attacking the logarithms. And now we're going to go into how do we read regression output data where we've had re-expressions done. Alright, now this is the stuff that we covered in cases 1 through 5 in the ladder of powers. That's all stuff that we would do in the field in real life. You know, if we get data, not all data is going to be linear. We got to re-express it, and obviously you've done that in some of your former classes. If you haven't done it here already, obviously every set of data that you get is not going to be linear. So we are going to use other models. Okay, but the stuff that we're going to do right now going forward is all the stuff that's basically going to be on the AP exam. So the AP exam is all about interpretations of this type of stuff. Very rarely are you going to be asked to actually do a re-expression. So this is how an AP problem would be presented to you. So you got bass is a type of fish, and the length and the weight of the fish, and length in centimeters and grams, and they graph it, and you can see there's a distinct curve there, and then they show the residual plot, and obviously there's a distinct pattern there. So they say, well, we'll comment on the appropriateness of a linear model. Well, we look at the scatter plot, it's curved, and the residual plot shows a pattern. So we would say the scatter plot between length and weight of a bass not a bass, but a bass shows a curved pattern, and the residual plot also shows a clear path, also shows a curved pattern. So a linear model is not appropriate. That's it. So the scatter plot's not straight enough, and the residual plot shows a pattern. Linear model is not appropriate. So now what they did is they did log weight versus log length. Okay. So comment on the appropriateness of a linear model. Well, the scatter plot of bass that has log length versus log length is straight, positive, and fairly strong. And the residual plot is random. Therefore, a linear model is appropriate. Okay. So that's how we would answer that question. Those are two typical questions on the AP exam. Okay. Now we go to the next part. Now we went through this last chapter. Okay. You need R squared. Do not worry about R squared adjusted. Okay. You're not going to deal with that. This thing that's next to the constant here is your y-intercept, and this thing that's right below it is your slope. Now, in this model, we're using length to predict weight. Okay, length predicts weight. So, we re-expressed it. So we have log of predicted weight equals our y-intercept, negative 1.8994, plus 3.04942 times the log of length. Okay, our re-expression must be done in terms of log and log. Comment on the strength of the model. Well, when we talk about strength, we're going to talk about two things. We're going to talk about correlation, and we're going to talk about R squared. Well, R squared is 99.9%. So, do you remember what R squared was about? It's about one word: variation. It's the variation in this. So what we would say is 99.9% of the variation in the weight of the bass is explained by the least squares regression line. Okay. Actually, that's let me rephrase that. Okay. 99.9% of the variation in log of weight. We have to do everything now in terms of our re-expression is explained by the variation in log of length. I can no longer say simply 99.9% of the variation in the weight is explained by the length, because that's not true, because weight was re-expressed as was length re-expressed. So when I interpret anything, I must interpret it in terms of the re-expression. So again, when I answer this question, I talk about strength and I talk about R squared. I'm going to say 99.9% of the variation in the log of the weight of the fish is explained by the variation in the log of the length of the fish. Okay. Now the other thing I'm going to do is I'm going to take out my calculator and I'm going to do the square root of 0.999 because I want the correlation. And it comes out to 0.9995. Okay, so R, we talked about R squared is 99.9%, and we just explained that, and our correlation is 0.9995. So correlation tells us two things. It tells us the strength and direction of a linear relationship. However, this linear relationship was re-expressed. So when we interpret this, we must do it in context of the re-expression. So my correlation, what I'm going to say is there is a strong, positive, linear relationship between the log of the weight of the fish and the log of the length of the fish. I cannot say there's a strong, positive, linear relationship between weight and length, because that's not true. If we look at our scatter plot, there's weight and there's length. There's not a strong, positive, linear relationship. There's a curved relationship. So I had to talk about it in terms of my re-expression that I did down here. So I had to talk about that in terms of log weight versus log length. Okay? Interpret slope in context. Okay? So my slope is 3.04942. Okay? So what this is this now means when I look at this line, when this here on this axis goes up by 1, this here goes up by 3.04942. Well, what is this 1? That's log of length. So when log of length increases by 1 centimeter, well, what's this here? The log of the weight of the fish increases by approximately 3.05 grams. Notice in my interpretation, I did it in context. Okay, so when log of length increases by 1 centimeter, I didn't say when length increases by 1 centimeter, I said when log of length increases by 1 centimeter, then the log of weight will increase by approximately 3.05 grams. You could also say, to start that, you could say the model predicts that these things will happen. Okay, that might not be a bad way to phrase it. Okay. Okay, interpreting the slope in context. I mean the y-intercept in context. That's something that is going to be very difficult to do here, since this thing, I can't put 0 in here, right? So this isn't a typical question I would ask you to do, but what we can do is, I can't put 0 in here, because if I put 0 into log, watch what happens. We do log of 0, well, it comes out, it's a problem. But what I can do is I can put a very, very small number in there and approximate this. So I'm going to make this negative 1.8994 plus 3.04942 times the log of 0.00001. Okay, so I just put a really, really small number in there. Okay, and I get negative 29.34. So basically, I have log of predicted weight equals negative 29.3444, and then I do base 10 to both sides, and I get this. What is that? Well, that's 4.53 e to the negative 30th. Well, I'm not going to write that out on the paper. That's a decimal with 29 zeros and then 4527. Well, what is that really? That's really close to 0. Okay, so what this basically comes out to is the predicted weight is approximately 0, and that's what we would expect to happen, by the way. If we had a fish with no length, we would expect the weight to be about 0. So this is basically how we would write this up. We would say when the length of a fish is 0 centimeters, then the model predicts that the weight will be about 0 grams. Okay. However, there are no fish swimming around that are 0 centimeters, so this is an extrapolation. If we look at our data, our smallest length is 5.2 centimeters. So again, this is just a basis to start the model, but it really has no relevance in terms of making any kind of predictions or anything like that. Okay. And then we got to do the residual for a bass that's 25 centimeters long. So residual, that's going to equal our actual. So let's go here on our chart, and there's the bass that's 25 centimeters long, and he weighs 264 grams. And then we got to figure out what the predicted is. So let's do that. Okay, so let's figure out what this is here. So we're going to do a 1.8994 plus 3.04942 log of 25, and that's 2.3635. So log of predicted weight, that's 2.3635, and then we got to do base 10 to both sides. So I'm just going to do base 10 raised to the answer, and I get 230.94 grams. So the predicted weight is 230.94 grams. So 230.94. So we do 264 minus 230.94, and we get 33.06. So what does that mean? That means that the fish weighed 33.06 grams more than the linear model predicted. Okay, so that's how we would interpret that in context. So that in itself, what we just did on this page, is basically what you're going to typically see on an AP exam. Okay.